Great. Share the screen. Open up the work, and here we go. Can I write? Yes, I can. And zoom in, and okay. Trigonometric ratios of general angles. Use a calculator to find each. Round your answers to the nearest 10,000. So I'm armed with my scientific calculator, and I'll begin with cosine of 101 degrees. It reads negative 0.1908089954. So I need it to the nearest 10,000. So for the first one, I'm just going to write it out in full. What my calculator actually says, it says 0.1908089954 ... Okay, the ... is a recognition of the fact that this is just going to carry on forever. Okay, and in a non-repeating and messy way because it's an irrational number. Anyway, I need it to the nearest 10,000th. So what does that mean? If I were to say negative 0.2, that would be to the nearest 10th. If I were to say negative 0.19, that would be to the nearest 100th. Negative 0.191, that's to the nearest 1000th. And negative 0.1908, that's to the nearest 10,000th. My decider digit is the 5th digit. And because this is a 0, I don't change this 8 right here. Okay, so I just simply write this. Cosine of 310 degrees. Type it in. You see on your calculator 0.64278. There's an 8 at the end. So it's closer to the truth to say 0.6428. Okay. Sine of 105 degrees. We have an exact number. Root 6 at root 2 over 4. You may notice that 105 is 60 plus 45. And sine of 60 and sine of 45 are two exact values. They're two things that you know. And you can actually deduce what this is using the angle addition formula. But that's to come later. To comply with the instructions here, you actually have to turn this into a decimal. So I press the S to D button on my calculator, and I get 0.659, the nearest 10,000th. Another way, 0.9659, I meant to say. Another way to say this, 4 dp, 4 decimal places. This here means sine of negative 305 degrees, which we interpret as a clockwise motion through the 3 quadrants, and then an extra 35 degrees. But we can just type it in, sine of negative 305 degrees, and we get 0.8192. 0.8192. The next 4 are going to be very similar, so we're just going to rush through those. 0.7431. This will be an exact number. This is negative root 3 over 2. Try to write these down when they're exact so that you get used to this. and it's negative 0.8660. Cosine of negative 70 is 0.3420. Cosine of 140 is negative 0.7660. Now, we've encountered two exact trigonometric values so far. Sine of 105 degrees and sine of negative 120 degrees. Here, we see many more are expected of us. So let's remind ourselves about how that works. Let's open up my room, just a little dashboard here, a little whiteboard, an online whiteboard service. And let's remind ourselves about what the exact trig values are that we are expected to know. Okay, so if you type in exact trigonometric values, the results that you'll get are like you'll see a table with 15 cells in it, and they'll have complicated expressions inside, and it seems overwhelming. And sometimes you even see tables bigger than that. The better approach than just looking at those tables and trying to memorize them and just reciting them over and over and over again is to really try to think about the structure involved, okay? And to try to understand what sine and cosine actually mean. You will be surprised how many students graduate or pass like a mathematical course and solve trigonometric problems, but when you ask them, what does sine of 37 degrees mean? They have no idea. They can't tell you. So let's be clear about what sine of 37 degrees actually means. And we're going to start at the very top. Trigonometry. What is it? Trigonometry is the study of triangles. I wish it were called triangulanometry, or I wish triangles were called trigons. It would make so much sense. The study of triangles. Questions using different mathematical techniques. If there's such a thing as trigonometry, the study of triangles, is there such a thing as pentagonometry, the study of pentagons? Or how about hexagonometry, the study of hexagons? No, those fields don't exist because pentagons, hexagons, octagons, etc., can always be broken down into triangles. A triangle is a three-sided shape. It's special. Things can be broken down and reduced to just a bunch of triangles stuck together. So it makes sense that we would have a whole area in maths just dedicated to understanding triangles. Now that we understand that triangles build up everything, build up all the shapes in space, what triangles are like more special or fundamental than others? Perhaps like an equilateral triangle, right? Where all the sides have the exact same length. Like take 3 matchsticks and you make an equilateral triangle, right? Sounds good, but not quite. The most fundamental like group of triangles are the right-angled triangles. The right-angled triangles. Right triangles, that's like their short name. These are more special than all the other kinds of triangles. Here's why. Make a totally random triangle for me. Okay, there's a random, totally random triangle. If it's completely random, we have no reason to think the sides are the same length or the angles are the same. They're all different. So we call it like a scalene. A scalene triangle. The thing is, you can always do this. You can always break it up into a pair of right triangles stuck together back to back. Therefore, if we can understand right triangles, we unlock every other triangle. Every other triangle. Incredible. But there are a lot of right triangles. There's a lot of right angle triangles. So the next question is, what right angle triangles are special? What right angle triangles are special? And I propose that I propose the following. When we look at a right angle triangle, we understand that it always has a longest side, which we call the hypotenuse, and a pair of shorter sides, which we call the legs, of the right triangle. So the hypotenuse is like special. It's like built into the right triangle. And what could be more special and more like basic and foundational than the number one? The number one. Let's consider the right angle triangles who have a hypotenuse that is exactly 1 unit long. 1 unit long. Okay? That means the two shorter sides, the legs, are going to be like decimals in between 0 and 1. So this will be like 0.87, and this will be like 0.64, whatever. I'm just making these numbers up. I don't know if that's true. Okay? But that's how it's going to be. Now, we understand now why our focus is here, right? So many possible shapes out there, so many possible things that you could consider. Why are we looking just at this? Because once we unlock these things, we unlock all right triangles. And once we unlock all right triangles, we unlock all other triangles. And once we unlock all the triangles, we unlock all the other shapes in the universe. Amazing. So we only have to understand unit right triangles. These guys who have a hypotenuse of length 1. They're special. Just to really drive that point home, imagine if I had, no, in fact, I'll do this just to really like emphasize what I'm talking about. I'll make an exact perfect copy. And then on this little control here, I'll drag it out. So the hypotenuse no longer has a length of 1, obviously. maybe it has a length of something like 3. I think I made it about 3 times bigger, right? But clearly the triangle is just a zoomed out version, like it has exactly the same shape. The mathematical word for that is similar. These two triangles are similar. Even though one is bigger than the other, they essentially have the same shape, same proportions, you know? And like, if I know what the length of this leg is here, you know how I could get the length of this leg, of this big one down here? Like, imagine if this was like 0.6. Just imagine. All I've got to do is times that 0.6 by 3. Just times it by 3. And this is 1.8. Amazing. So, so that sort of cements now and makes it very clear why we're looking at unit right angle triangles. Now, if we have a unit right triangle, wouldn't it be tremendously useful if we had a way, oh, and we know the focus angle down here in the corner, like let's just say it's 37 degrees, right? Wouldn't it be tremendously useful if we had some kind of machine that could just magically give us the exact length of this side, whatever it happens to be, right? Because I don't want to have to draw out this triangle using my ruler and protractor and then, you know, just basically guess the length of this side by trying to measure it, even though I'm not going to get it very accurate anyway, right? Wouldn't it just be better if there was a machine that could do that for us? And wouldn't it be better if there was a machine that could find the length of that side for us? And guess what? There are these machines. And remember, a mathematical machine is called a function. It takes in an input and gives you an output. There's one function called sine, and there's one function called cosine. And if you feed sine 37 degrees, it will tell you the length of the side that is opposite the focus angle in this unit right angle triangle. If you feed sine 37 degrees, it will tell you the length of the side that's opposite the focus angle of 37 degrees in this unit right triangle. Cosine, its co-worker, tells you the adjacent side. So let's establish that fact. Sine of 37 is 0.6018. And cosine of 37, obviously it's going to be bigger, is 0.7986. How do we know that our functions are actually doing their job? We use the Pythagorean theorem. Square this side, add them together, and you should get 1. Let's see, 0.6018 squared plus 0.7986 squared equals 0.9999. Why is it not exactly 1? Well, because I rounded them. I rounded them, of course. Okay, so now that we understand what sine and cosine actually are, now that we understand what they actually are, we don't feel like we're just mindlessly memorizing. Okay, because I'm about to tell you and talk about exact trig values. Okay, so it's on now that focus angle down in the corner, which in this case happens to be 37 degrees. What could it possibly be? Well, it could be any number from going from 0 degrees, which would be like a really, really, really flat triangle. Like anything close to 0 would be really, really, really flat, all the way up to 90 degrees. So imagine if that 37 degrees turned into 89 degrees. So it'd be a really, really skinny and tall triangle, right? But in maths, we consider like the extreme cases as like legitimate, you know? So if it was literally 0 degrees, then that opposite side right there would shrink down to 0 itself. It would be 0 units long. 0 units long. So sine of 0 degrees is exactly 0. And if it were 90 degrees, imagine that. That opposite side there would get longer and closer to 1 and longer and closer to 1 and longer and closer to 1 until it reaches 1 itself. And the hypotenuse and the opposite side become literally the same thing. 1. What about 45 degrees? Surely that's special, right? Yeah, it is. And you can actually work that out yourself. You don't even need your calculator. So I'm going to draw that unit right angle triangle. There it is. And the focus angle is 45 degrees, and therefore so is this one, 45 degrees. So it's an isosceles right angle triangle, very special indeed. And so if I call that missing mystery side x, and that one has to be x as well. So working out the lengths of that is just straightforward application of Pythagoras. And it turns out to be root 2 over 2. Then 30 degrees, 60 degrees. These involve more sophisticated arguments, but you can get into them in your own time by yourself. So this one here is exactly a half. This one here is root 3 over 2. And then cosine is the complement of this. The complement. This row in the table reads backwards. And the tangent, that you obtain by dividing the length of the opposite by the adjacent, and therefore in the unit rectangle triangle, it's literally sine of theta divided by cosine of theta. So 0 divided by 1 is 0. A half divided by root 3 over 2 is 1 over root 3. Root 2 over 2 divided by root 2 over 2 is 1. This is root 3, and this is undefined or infinity, however you like. With all that said, I mean, I'm going to get into the questions now. Okay. Because I really want to. Find the exact value of each trig function. Some may be undefined. Find tan of 2 pi over 3. Okay, so I convert them to degrees. So 2 pi over 3, well, that would be 120 degrees. At 90, it goes up, and then it wraps it back around, so 120 degrees. That'll be the negative of tan of 60. So negative root 3, I believe. Let's check if I'm right. Yay! Actually, secant of negative 3 pi over 4. Okay. So that's 1 over cosine of negative 3 pi over 4. Now, cosine is an even function. That means cosine of a negative x is equal to cosine of x. Basically, it's symmetric about the y-axis. So 1 divided by cosine of 3 pi over 4. And pi is 180. So 3/4 of pi is 135. So cosine of 135 degrees. Let's see. That goes down 135 degrees. So goes 0 down to 90. Root 2 over 2, negative root 2 over 2. 1 divided by negative root 2 over 2, that's negative 2 over root 2, I believe. Let's check. No! Really? How is that not right, though? Let me think. Oh! Oh my god. What is 2 divided by root 2? Negative root 2. Like, what is negative? Yeah, of course. It was right. Okay. Just being stupid. Okay. So, cosine of 11 pi over 6. Okay. So, that's... So, it goes 0, then 90, then 180. And pi is 180, sorry. And then it goes back up. So then it goes to 9 pi over 6. And then there. So basically 2 pi here, whatever this is. So 1/6 of pi. Well, so 30 degrees. Yeah. So 30 degrees, so root 3 over 2. Okay, check. Oh, hooray. Cotangent of 5 pi over 3. That's 1 divided by the tangent of 5 pi over 3. And let's see. 1 2/3. So 180 so 300 so 90 180 270 and then 30 up from the negative, which is the negative of tan of 60, and tan of 60 is root 3, so negative 1 over root 3. Which, if we rationalize the denominator, yes, is negative root 3 over 3. Okay. Cosecant of negative pi over 2. Well, that would be 1 over sine of pi over 2. Of negative pi over 2. Now, pi over 2 is 90 degrees. And so negative pi over 2 is negative 90 degrees. And that's going to be negative 1. So it'd be negative 1. Yay. Tangents of negative 3 pi over 2. 3 pi, okay, so 2 pi is 360. So 1 pi is 180. So 1.5 pi must be 270. So this is tan of negative 270 degrees. So how does tan work? It shoots off to infinity at 90, wraps back around, climbs up to 0 at 180, then shoots off to infinity at 270. But wait a minute, they're asking us to go to the negative direction. Uh-oh. Okay, fine. So goes down to negative infinity at negative 90, comes up from positive infinity, climbs, goes down to 0 at negative 180, and down to negative infinity at negative 270. So we say undefined, but we really know that it like tends towards negative infinity. Let's check. Yay, did it. Okay. Secant of 0 whatever, 0 degrees, 0 radians, doesn't matter. That's 1 over cosine of 0. And cosine of 0, well, that happens to be 1. And therefore, this is 1. Tangent of negative 7 pi over 4. So that's like negative 1 3/4 of pi. So 3/4 of that. So it's 45 degrees less than negative 360. So in other words, like 315. So anyway, all right. So it goes down to negative 90. So down negative 90. Okay. 0 and 180. Down 270. Okay. Comes down at 360 there, like that. So I'm visualizing like that. And we want like the halfway point. So 1, is it just simply 1 and 1? We check. Okay, good. Now Who's next? Okay. Find out secant of theta. And the point here is 13, -9. Okay, but these aren't exact values. No, they're not exact values. They can't be. Well, I mean, no, anyway, whatever. So, secant of theta is 1 over cosine of theta. Now, cosine of theta from SOHCAHTOA is adjacent over hypotenuse. So, secant of theta is hypotenuse over adjacent, right? And the hypotenuse in this case is 13 squared, add the square root of -9. So 169, add 81. So that's 170, 250. So yes, root 250, which is 5 root 10. 5 root 10. And wait, am I actually supposed to do this? Yeah, I think so. 5 root 10 then is the hypotenuse. So hypotenuse over adjacent, so 5 root 10 over 13, I think. Let's check. Amazing. Okay. Sine of theta in this case. Okay. Right. Well, that's okay. Sine from SOHCAHTOA is opposite over hypotenuse. The hypotenuse in this case is 16 at 256, which takes us up to 272, which that's 16 times 17, obviously. So that's going to be 4 root 17. That's the hypotenuse, 4 root 17. So it's minus 16 over 4 root 17, which is minus 4 over root 17. And then we want to rationalize the denominator as a courtesy, why not? So the negative of 4 root 17 over 17 itself. I believe that's right. Oh, yay. Awesome. All right. Okay, cosine of theta in this case. Let's get the hypotenuse. 4, 5, stick them together. You get 9. Square root that. You get 3. And we need the cosine of this theta here. So, using the definition, adjacent divided by hypotenuse. So, what is the adjacent? Is it simply -2? So, is this really just -2 over 3? We'll check. Yes. Okay. Sine of theta. Okay, hypotenuse 16 for that one. Square that. Okay. 4 times 5, that's 20. 20 and 16, that's 36. And then 36 square rooted is 6. So, -4 over 6, so -2/3, I believe. No, wrong, because it's the opposite. Okay, so that would be negative 2 root 5 over 6. So negative root 5 over 3. How about that? Oh, yay. Okay. Cosine of theta in this case. 64 add 17 makes 81. 81 square rooted is 9. And so adjacent of hypotenuse 8 over 9, I believe. Yeah. And here, what is the hypotenuse in this case? Well, 16 squared, I mean, come on. When you add those two together, you get 512. So it's going to be 16 root 2. So 16 root 2, so adjacent over that, so 16 over 16 root 2, so 1 over root 2, so root 2 over 2. Okay. How about that? Yeah. Awesome. Okay. Next up, I'm going to do this one. Finding the length of each arc. Okay. So the circumference of a circle, as you know, is pi d. Pi times the diameter. What if I want to find an arc? And the angle of the sector defined by the arc is theta. Well, I think you would do theta over 360 if theta was given in degrees, and then times that by pi and that by the diameter, and that would give you the arc length. So I could call it arc. No, I'll call it L arc. Okay, so let's just do the calculation here. Pi times 22. Yeah, I know, that seems way too blimmin' big. So what am I doing here? Oh my goodness me, I've got the reciprocal. No, wait, I didn't. It just didn't register when I typed in 360. So 77. You know, I should really like catch errors before I check. Okay, let's try this again. So 77 over 4 pi is about 60.5. So pi d, 3/4 of pi d. That makes sense. Right, areas of sectors. There's more. For areas of sectors, you just have to find the area of the entire thing and then multiply it by what fraction that is. A sixth, and so the area of the entire thing is, so that's pi r squared, so that's 100 pi, 100 pi, 1/6 of 100 pi. It's 50 pi over 3. To the nearest tenth, that's 52.4 square inches for this one here. Okay, pi r squared, so 9 pi, and then 150 over 360 is 15 over 36. 15 over 36, that's 5 over 12. 5 twelfths. Of 9 pi. 45 over 12 is 15 over 4 pi. Obviously, this is 3/4. So 16 pi. So 3/4 of that. 12 pi square centimeters. Seventeen over 24. I think is it really, unless like I'm messing this up. 833 over 6 pi. Okay, wait. Fine. Square yards. 436.2 square yards. And over here we didn't get the 12 pi. 37.7. And over here we didn't get the 15 over 4 pi. It's 11.8. Right, okay, so now these ones have to be exact. So, pi r squared, so that would be 256 pi, and then it's 2/3 of that. So 512 over 3 pi, that many square feet. This one's 315 over 360. And so that is 7/8. And pi r squared is 196 pi. And 196 times 7/8. So that's the same thing as 98 times 7 over 4, which is the same thing as 49 times 7 over 2. 49 times 7 over 2 is 343. Yeah. $196 pi times 7 over 8. Pi r squared. 196 pi and 3/4 of that. $49 triple 147. I think. So it's like 19 over 24 parts of a circle. And pi r squared is 144 pi. You can cancel out that 12, so 19 over 2. Times that. And then cancel out the 2, so 19 times 6. And then 6 times 19 is 114. Not many square feet. Pi over 2, that's 90 degrees, and the radius is 10 miles, so pi r squared, so that's 100 pi, so 25 pi square miles. We have a circle whose radius is 12 yards, and the angle in question, and the angle of the sector is 5 pi over 3. 5 pi over 3, that's 1 2/3 pi, so that's 5/6 of a circle. It's 5/6 times 144 pi. And 144 over 6 is 24. And 24 times 12, no, 24 times 5 is 120. $7-kilometer radius, so 60 degrees, so that's 1/6. So 49 pi over 6. That many square kilometers. 225 degrees. Well, that would be 5/8. Times that by 49. So I mean that's 245 over 8 pi mile square miles. Okay. Coterminal angles. Right, find the reference angle. Okay, I'll check like a page at a time. All right. Okay, so in that quadrant there, so I believe it's going to be 50 degrees. $360, $450, $540, $630. I believe that's 50 degrees. That's correct. That's correct. Okay. $30 degrees. That's the reference angle, reference angle, reference angle, reference angle. And here, like an 18th of pi. And here, 12th of pi. And here, state if they're coterminal. Okay, so if the separation is a multiple of 360, then the coterminal. So the separation here is 185 and 545, which is 730. So no. And the separation here, $161 takes 17, so that's 151, and that's 144. 144 is divisible by 36, so yes. And now find a coterminal angle between 0 degrees and 360 degrees. Okay, but first, let's just check these. Okay, that's good. We have them. So isn't it just simply 30 degrees? Yeah. Negative 435. So that would be an extra 75. So the coterminal angle is, so why is it not 75 itself? I think it is. For this one here, don't you just do sort of like mod? So I could just... Wait, am I getting this? Right. So they've said 285. But I said 75. So what's wrong with that? So we know it's going to do that. 360. Then there. Oh, right. You have to go around the other way. I see now. Of course. Right. Okay. Fine. Fine. Okay. So this one's going in the normal direction. So we really just 640 mod 360, which is 280. But for this 442, negative 442 degrees, you go around once, and then you're at 360, and then there's an extra 82 degrees to go, so you end up like there-ish. Okay? But you need a coterminal angle that's between 0 degrees and 360 degrees. So you have to go around anti-clockwise. So it's going to be 270 plus. Now that separation there is 8 degrees. So 278 degrees, I believe. Okay, excellent. Got that. Now find a coterminal angle between 0 and 2 pi for each given angle. Okay. Five pi over 3. Isn't it just 5 pi over 3? And for this one, Okay, I think that's right. Find a positive and negative coterminal angle for each given angle. I mean, isn't the positive itself? Not actually sure what this is talking about. Like, find a different one? Okay, so they've asked for a different one. They should have said that. So it's 13 pi over 4. That's adding on 8 to the numerator. And then this one, adding on 72 to 25, that would be 97. Okay, and the negatives. Now they say negative 3/4 of pi. Right, I get it. Because I have to, the absolute values of them have to add up to 2 pi. Okay, so for this one, shouldn't it be negative 9 pi over, no, negative 11 pi over 36, right? Oh, my goodness me. Okay, 36 plus 11, because it has to be 72 pi. Right, okay, so negative 47 pi with 36. Right, I get it. It's just a bit of fatigue, that's all. A little bit of fatigue. But overall, we're doing all right. Okay, we're going to take a break here and be back in a second.